The financial market is a market in which people trade stocks, financial securities, and other items of value. This market is inherently defined by its volatility and risk. For the past few decades, mathematicians have been trying to model this market, attempting to predict the prices of financial commodities and optimal trading strategies. But how do we even model something that we ourselves couldn't fully predict? Something that is random. Brownian motion was an answer that they came up with. The Brownian motion was first discovered by biologist Robert Brown. While examining pollen grains under a microscope, he observed small particles ejected from the grains moving in a continuous, random, and jittery way. He found the same pattern in particles of non-living matter, thus ruling out the possibility that this effect was somehow life-related. This motion is then formally captured by mathematician Norbert Wiener by the Wiener process. However, this process is still most often referred to as the Brownian motion today. The Brownian motion itself is actually quite simple to understand. Its essence relies on the idea of normal distribution. Normal distribution, or often known as Gaussian distribution, is a probability distribution. In simple terms, this is a distribution in which something random achieves one particular value with highest probability. And as we deviate from that particular value, the probability becomes less and less. Therefore, when we plot this graphically, we see a bell-shaped curve. To better understand normal distribution, we could consider an example. Height of population could be considered as a normal distribution. When given a random person and we do not know his or her height, we would have some rough estimate in our mind. This is because most people have heights within a certain range. And it is an educated guess to assume that that random person also has height within that certain range. And we'll be surprised to see if this person is extremely tall or extremely short. And if we're able to extract the guess and somehow plot it, we see in the middle, within a certain range, it has a very high probability, and as we deviate, it has a very low probability, thus giving us the normal distribution. Normal distribution is essential in the statement of central limit theorem, which states that under certain conditions, averages of many independent random variables converge to normal distribution. For example, if we think of a coin toss result as a random variable, then if we toss this fair coin 1,000 times, we would expect the total number of heads to be around 500, about half of the total number of tosses. We wouldn't be surprised to see something like 490 heads or 510 heads as the result, because it is still in that ballpark. But we would be more and more surprised to see 400 heads, 200 heads, or 1 head as the total, because these results are increasingly harder to achieve, considering that we indeed have a fair coin. So if we consider head as the value 1 and the tail as the value 0, the distribution of the average of these values should be a normal distribution centered around 0.5. Now, after getting intuition about normal distribution, the Brownian motion should be very easy to understand. There are 4 criteria for a process to be Brownian motion. First, the process has to start at 0, whether it be 0 on the real line or the origin in the Cartesian plane. It is simply fixing the process to start at a preferable value and is not essential for our understanding of Brownian motion for now. Second, the increments of this process are independent, meaning taking any 2 time segments, the 2 segments of this process have no effect on one another. When we track back to what Robert Brown discovered, this definition should be very intuitive. While you have a particle in pollen grain waters moving around, the motion of this particle in the coming second shouldn't really depend on the motion of this particle in the past second, because the particle could be moving in any direction and it could hit any number of pollen grains that exerts force in any direction to redirect this particle. Third, the increments of this process are random and follow a normal distribution. Again, if we go back to what Robert Brown observed, this should make sense. We see that there are so many of the pollen grains in the water, so that the force that this particle is affected by at a particular second is actually an average of a great number of independent random forces. It should become apparent that the particle is most likely to stay around the ballpark of where it used to be, but with a small chance it could dash in a particular direction when all of the pollen grains happen to exert force in a similar direction, thus giving us this normal distribution property of Brownian motion. Lastly, the fourth property of Brownian motion requires the motion to be continuous. Of course, examining Brown's example, despite the random motion of the particle in pollen grains water, it is impossible for it to jump from one position to another instantly. So the motion is of course continuous. Now, after overviewing the four properties of Brownian motion, let's see how it could be applied in the financial market. Let's take one of the simplest and most common financial commodities, stock, as our example. Why would a Brownian motion be a useful tool here? We see the essence of this randomness in the stock price is actually perfectly captured by property 2 and 3 of Brownian motion. Increments or decrements of the stock prices of one particular time segment are somewhat independent of its increments or decrements in a separate time segment. And these increments or decrements could be considered as random variables following a normal distribution. This is because there are so many buyers and sellers pushing the prices up and down at each individual second. To make an analogy, if the stock price is the particle we're considering in Brown's example, then the traders are simply the pollen grains. When there are a lot of these forces, the stock price tends to stay in the ballpark of where it used to be. But it could also jump up or down drastically in rare situations. Of course, the Brownian motion itself isn't perfect in describing stock prices. Mathematicians and financial analysts often use geometric Brownian motion for the portrayal of stock prices, but that will be a topic for another day. Thank you so much for watching the video, and if you have reached this point of the video, you're probably just as passionate about the subject as I am. I would appreciate it if you could leave me some comments or email me directly to give me some feedback. Thank you so much again.